Great pleasure to welcome a new fleet of recess interns this morning. We're so pleased to have you here. This has become my favorite time of year because the energy level and the noise level escalates, and I really enjoy the energy. And I know that each of you has worked very hard to be competitive in this pool. The recess internship program has gotten progressively more competitive year by year. So as we have been able to advance both the academic standards that we set in selecting you, at the same time bringing in large, vital, and diverse cohorts to move all of these things together is a testament to your hard work and your engagement with this field that has enchanted you. And I was lucky to get to read some of the applications this year because we were between directors, and so it was all hands on deck for selecting you. And I was very impressed, having not been directly involved with the selection process for several years. So congratulations to each of you on your accomplishments that brought you here. We're really glad to have you around and to boost our energy during the summer. So thank you. Okay, so next it is my great pleasure to introduce Rob Reilinger, who is going to present our seminar today. He received his bachelor's degree from Villanova University in physics with a minor in mathematics, and his master's in physics with a minor in astrophysics at Cornell, followed by a PhD in geophysics at Cornell. And he worked with Dr. Jack Oliver, who is, of course, one of the early leaders in reimagining the dynamics of the planet in the plate tectonic paradigm. So I didn't actually know that about you. So he continued working at Cornell in a research capacity for 4 years and then moved to MIT at Earth, Atmospheric, and Planetary Sciences, where he spent for 28 years in a group that I was privileged to spend a sabbatical with some years ago now. So Rob is an animal when it comes to field observations. His passion has been around GPS and also INSAR, the radar interferometry imagery that integrates so powerfully with GPS. His early work focused on the San Andreas Fault and other active areas of the western U.S., but most of the time I've known him well, he's been deeply involved in observations in very difficult places to work in Arabia, Africa, and Eurasia plate interactions and the kind of the greater Mediterranean region. So his focus has been on the solid Earth, the dynamics of plate motions, lithospheric rheology, and earthquake and tsunami and volcanic hazards. He's published more than 65 papers in the peer-reviewed literature, and I know him personally to be one of the strongest empiricists that I've ever met. He's all about getting the data and getting it under incredibly difficult situations. In fact, a couple of years ago when I saw him, he had been working in the Middle East and had been participating in the daylight fasting of his collaborators, and was looking a little hungry at that point for almost a month in order to be able to collect these observations and also really connect with the cultures and the scientists that he works with. He's been a very passionate and yet pragmatic advocate of open data and has really led in the international realm in that. And I think I will hand it over to him. I think he'll be very pleased to hear about both some of the early history. Oh, I should add that UNAVCO is recognizing that 2014 will be our 30th year as an organization, if you count the different management structures that we have operated under. And so as part of that, we are documenting some of the early work, and Rob was asked to address that as part of his presentation. So please join me in welcoming Dr. Rob Reilinger.
Thank you, Megan. And I was going to thank you all for coming, but I think you're a captive audience. But it's a nice opportunity for me to talk about work that I've been involved in for some time. And contrary to what Megan said, yeah, they're difficult sometimes, but a lot of fun. I've had an amazingly lucky career, and it's been a great opportunity to visit some great parts of the world. So, that's my title. We're going to talk about GPS, and I didn't necessarily design this talk for non-geologists, so if you're not a geologist, you're going to have to pay real close attention in the beginning when I rush through a few things. But what we do with GPS, what I do is really not difficult. Mostly it's the hard work is what a lot of you guys at UNAVCO do, and what a lot of my partners at MIT do, which is the data processing and the quantitative modeling studies. So as Megan said, I'm an empiricist. I look at the pictures and I try to figure out what's going on. I don't know if you'll ever be able to get away with murder like that in your careers. Things are changing quickly, but really it's been a pretty lovely experience. So this is the kind of pictures we're going to be looking at, and this is just a view of a very decimated velocity field. This is showing motions. Each one of these arrows is the motion of that particular point at the base of the arrow, and measured with GPS over the course of some years. So we're going to look at pictures like this and see what we can, if we can figure out. What are the main forces driving the plates? What is the main forces causing deformation in the interplate zone? So pretty much I'm going to assume you know about plate tectonics. And this, I thought this was going to go forward if I push that button. Not that. So, oh, look at that. Okay. So before I start the talk, I wanted to acknowledge the UNAVCO field engineers I've had the privilege and great fun to work with. I've never met a UNAVCO field engineer I didn't like. This is not a total complete list, but I think I'm missing one or two people who worked with us in Southern California in the earlier days, but this is most of the guys who worked in the Middle East and in Turkey and Greece and that part of the world. And I'm very grateful, and couldn't have done any of this work without the help of this institution and these great partners. And we've worked in quite a few countries, and so these are a list of our principal collaborators from each of these countries. I think there's 18 countries. And a lot of friends, a lot of good friends. And really, each of these individuals was personally dedicated to work on a combined effort. Each one has their own individual problems. In Turkey, there's the North Anatolian Fault that causes very deadly earthquakes. That was the focus of their interest. In Azerbaijan, there's the Caucasus Thrust Fault. In the Middle East, there's the Dead Sea Fault. So each area has their individual geodynamic problem, their individual earthquake hazard problem, because this work relates to the earthquake hazard. The movements of the earth generate the stresses that give rise to earthquakes. But all recognized that to understand their problem, they needed to understand the problem on a broader scale. And that's where we try to make our contribution. And I did want to note that over the course of this project, we've installed some GPS stations, and each of these red, each institution individual marked in red is today contributing data to the global community. Okay, so I should have made my slides a little lower. Didn't anticipate that little green sign, but you can probably make it out. It's just the title of the talk. So I'm going to just spend a few minutes talking about GPS. We could spend the whole semester probably talking about GPS, but I'm going to give you the main thing you need to know, which is how precisely we can measure positions. That's basically all I wanted to know. How precisely can I, if I make a benchmark here and I measure it for 24 hours, how precisely will I know that position? And remarkably, we're now determining positions to about 2 millimeters in the horizontal and 5-ish in the vertical, and that's from 24 hours of measurements. So let's take a few minutes to talk about that. And the principal thing I want to get across here is what have we learned about the forces acting on the plate? So we're going to take a sort of step back and look in a general way at what are the system of forces that act on the plates. And this is work that's been done by a number of people, and I just listed a few of them here. Then, to give you a perspective, we'll talk about the regional tectonics of this plate system. It's Africa, Arabia, and Eurasia plate system, and virtually everything that you can imagine tectonically is occurring within that plate system, from rifting, subduction, major strike-slip faults, regional compressional continental deformation, extensional continental deformation. So it's a really gold mine for geologists and geophysicists to study geodynamics. And we'll conclude with try to put together what have we learned. Have we learned anything about the forces acting on the plates? And that's a very difficult problem. That's a problem that has existed since the advent of plate tectonics. And I think we're making progress. I'll let you decide whether that's the case. So geodesy, you can read here. You're working in the mecca of geodesy here at UNAVCO, so I presume you know all about it. It's the study of the figure of the Earth, both its shape and gravity field, and how the figure of the Earth changes. And geodesy has applications, as you can see. This is a nice slide that Simon McCluskey made for his job interview at Australia National University. Well, you can do tectonic plate motions and earthquakes. That's the kind of stuff we do. You can do Earth rotation. People like Tom Herring, other people use geodesy to study that process. Tidal motion and deformation, mass transport, changes the gravity field. You study the atmosphere with the GPS signals going through the ionosphere and through the troposphere. And man-made effects that cause changes in the gravity field or in the surface of the Earth. Pumping fluids, for example, causes subsidence. And all these things are being studied with geodesy. And in fact, geodesy, along with astronomy, is one of the most ancient sciences because you need geodesy to build roads and you need surveying techniques. And of course, the stars are up there. Everybody's looking at them. Can't miss that. So it has a very long history from ancient Egypt and continuously up to the GPS age. So GPS geodesy, this is the one slide introduction to GPS. It has 3 components. It has the space component, which is the satellites. It has a network of stations around the globe, excuse me, that track the satellites, and we need them in order to position the satellites. So we know the positions of these special stations on the Earth, and we can then invert that to determine the positions of the satellites. Then you have a whole bunch of strategies to take to estimate parameters and model all these different influences on the signal in order to determine the position of the satellites and then your position. So what you want to see here, I bet there's a pointer here, huh? No? Okay. Yeah. This one here? Laser. Yeah. Yeah. So the main thing here, this is the position of the east component of your position. So you have east and north, and it shows how that has improved over the years, beginning in the late 90s up to, well, if we went back to the TI 4100, we'd be up at here. So that came down very quickly here, and now we're down here. You can see about 1, 2 millimeters, maybe 3 millimeters. And these are all different analysis groups who all get basically the very similar result. And that goes hand in hand. Well, this comes from the very precise positions that we're able to deduce for the satellites themselves. So, plus or minus 2 millimeters in the present day in the horizontal. And pretty much we're using horizontal measurements. We have not really gotten much useful information out of the vertical from the work we've done in the Middle East and Mediterranean. Although there are some very important results coming now from this, particularly in the Alps, where they're measuring vertical motions over the last 20 years, I think about 1 millimeter a year. So that's quite important. But for us, no. So so this slide, which I swiped from the web, sort of is an overview of the different kinds of forces that are acting on the plates. And we have a force called the ridge push. So the idea here is that the hot material comes up here, elevates this part of the plate, and the plate sort of slides down by gravity, so that, in fact, gravity runs everything in the universe. And it goes down and slides off of this higher ridge. Okay, so that's a ridge push force, and this is one of the more important forces acting on the plates as we understand it. Another force is the slab pull. So what you have here is you have a hot plate, thin, it's hot, it moves away from the ridge where it's created, and as it gets further and further away, it cools, and at some point it gets more dense than the underlying mantle. At that point, it starts to sink, and so it sinks into the earth, and this is where, again, gravity drives that sinking, and this is where subduction occurs, this subduction zone. So this is another one of the principal forces, and the results of our studies are this is pretty much the story. Slab pull is what's driving the plates that are converging with Eurasia. So if you go to sleep now, it's okay, you got the main message. But there's some other subtleties here. Of course, there's lots of other things going on. This plate is, if there's a convective current in the mantle, that's going to either pull the retard it, can go in either direction. There's the resistance to the plate falling through the mantle. There are currents induced, turn out to be very important, in fact. For example, this is driven by, you might ask, why doesn't the plate go straight down? Why does it go down at an angle like this? If it's gravity, it's being pulled down. And in fact, it's these currents act on this plate the same as the air currents act on the wing of a plane and keep it pressurized to keep it up. So these are the forces, some of the things we're going to look at. There's the resistance to a continental collision. We've got that going on as well. So how much does this plate colliding with the continent retard its motion? These are the kinds of questions we're going to try to address. You see, I have a keypad issue. Got to be a way to do this. There we go. Okay, so that's the plate tectonic geodynamics slide, and now I have the active tectonics of our study area. So this is the area we're studying. The main plates are plate. They're separate. These little arrows here are really with respect to Eurasia. Now, this is something we're going to go through a lot of. We're going to show these same exact result velocities in different, what we say, reference frames. So if we're standing now on Eurasia, this is the way we'd see Arabia coming up towards us. We'd see this little plate Anatolian plate moving away this way. And we see Africa moving very slowly over in this direction, Somalia over in this direction. So that's if you're standing here. Now, if you're standing here, Arabia is not moving. You see, what would you see? You see Eurasia coming down towards you. You'd see Africa moving away from you because it's going, because you're going away from Africa. So look, so what you change is these arrows, depending on where you're looking from, but the difference between these arrows cannot change. And that difference, so that this plate will always be moving away from this plate, no matter what reference frame you look in. Okay, so the differences don't change, but the arrows themselves will change. You'll see this, I think. Okay, so let's go back to what we're seeing here. We've got Arabia colliding with Eurasia. So this is a continental collision. This is the Caucasus. We have convergence up here along the Caucasus, and we have you can see the topography. It's got smashed up and pushed up these mountains. This is the Zagros in Iran. This is the Eastern Turkey Plateau and the Caucasus Mountains. All of these and all the deformation here up through Iran, and these are these areas have all been get devastated by earthquakes. All of these are getting smashed up by Arabia. Over here we have these symbols. This is where there's ocean over here subducting. So here we have subduction, you saw in the previous picture, of this ocean material under Iran. Here we have this oceanic crust that's part of the Nubian plate subducting under the Hellenic arc here in Greece. We have big strike-slip faults, like this one right here. This is called the Dead Sea Fault, and these are the earthquake focal mechanisms. So we have the Dead Sea Fault, we have the North Anatolian Fault, we have the Caucasus Fault. And we have some funny business here. We have a little piece. This is no topography here, but this is oceanic, very very thick sediment pile, and at least part of the Black Sea is oceanic. And of course, this is Indian Ocean. So we have extension here along the Red Sea as Arabia moves away, an extension here, rifting, and in fact an ocean ridge forming in here and in parts here, very young, as Arabia moves away from Africa. And we have an East African rift, and you can see that that's opening very slowly. This arrow is going a little more westerly, this a little more easterly, so that opens up the rift, East African rift. So we got a lot of stuff going on, and we've got these basins in here, like this is the Aegean basin. It's a young basin that has been opened by a process called back arc extension due to rollback of the trench. And we'll look at a little, we might get to look at that a little more in some subsequent slides. So this is a couple of years old, but it's kind of the database, shows most of the database we're going to use. We have a lot more measurements now along the Dead Sea Fault in, where we go? This is Syria, this is Jordan, in Jordan. Otherwise, yeah, this is the database we're going to use. And again, look here, this is Europe. These are stations in Europe, Eurasia, and this goes all the way out to north of China. I mean, China's a deformation zone. Eurasia covers virtually a third of the circumference of the Earth, and all of that is basically stable. So you look at a GPS station here and here and here and here, and you don't see any motion between them. Meanwhile, you have these motions that we've measured here with the GPS. So this is the database we're going to use, and let's look at this in particular at the relationships up here between the motion as you go around this big arch. You can see the first order here. This is like a butterfly pattern. And it surely looks like this indenter has pushed all this stuff out of the way. But let's look at that a little more closely. So this is kind of a fun slide. And this is an old slide. And you can see there's a lot of data missing. And we eliminate some of the velocities when we want to look at things on this very broad scale. But in any case, it shows that nice butterfly pattern. It shows what looks like this big indentation, which is clearly an indenter. So this Arabia has squeezed into here, pushed up these mountains. But this deformation is occurring. Look at all this deformation that's occurring. You son of a bitch. I have to what? Oh, here. Okay. So this makes to me, this is a remarkable picture. Because look here, you've got these gigantic plates. This plate is gigantic. You see, these are the velocities on Eurasia. These are the velocities on Africa. This is another gigantic plate. In between, you've got all this rigmarole going on. So this is definitive. This tells you this is not plates backing into each other. This is stuff going on underneath that's churning up this whole business. And to me, that's maybe one of the most important lessons we learn by looking at things on this very broad scale. Now, look at this. This is curious, too. So we've got this thing indenting, right? It's smashing into Europe. But look, it's going 18 millimeters per year here. It's going 20, 21, 25, 32. It's getting faster and faster as you get away from the push. It's not a push. There's no way you can make it go faster here by pushing it over here. Not that I can imagine. If you can figure it out, please let me know. So there's something else going on here. But there was a push. You can't get away from the fact that this is a mountain that got somehow pushed up. Well, certainly here it's still a push. Look, you can see here it's getting, this is big, this is smaller, smaller. So it's squeezing here. But this is getting faster and faster over here towards, remember, this is the subduction zone. And this is the basin that opened up. So this is telling us that this subduction zone is more likely the cause for this motion than this push by Arabia. So that's fundamentally different view of what's going on here. You can see a lot in this picture, but we won't. So did I make all the points I wanted to make? Okay, so it's moving faster here. It's not being pushed any longer, but it was being pushed in the past. This is what we're looking for if we want to know about forces, because F equals ma. If it's no A, you're not going to learn anything about F, right? If the motions change, that means there's a change in the balance of forces. So this is what we're looking for. And sure enough, here, there must have been a change. What could have it been? Well, we're going to suggest that it may be that this big fault, when it broke all the way across, allowed this force of this trench to pull this whole plate out, almost without deforming it. And that's what's happening now. So we'll see if we can make that case. Okay. Happy with that one. Okay, but let's look then at the relationship. So we're looking for changes in motion. So let's look at the relationship between what we see today and what we can deduce from geologic observations. We can see offsets on faults. If we can measure something that was offset, date it, some dating technique, we can get how quickly that fault is slipping over geologic time scales. In some cases, we have the Red Sea. There's magnetic anomalies, and in the Gulf of Aden. So we can get plate tectonic estimates. Plate tectonics can tell you how rapidly things are extending by looking at the magnetic anomalies in the newly formed ocean. So we can make some comparisons, and that's what we've done here. This our models are the edges of our block model. So each one of these areas, so here's the Arabian block or plate. Here's the Sinai plate in here. The Anatolian plate we model as in here. We take our GPS data and say, well, if these are the boundaries, what would be the rates slipping on these boundaries? We remember we had Arabia going faster than Nubia. So we have a rate across the fault here. We can estimate what that is from the GPS. And that's what we do with this block model. And here we plot that, rates that we determine for different things, different tectonic features, southern Red Sea, Gulf of Aden, the Gulf of Corinth, that's over here in Greece, the North Anatolian Fault, that's this. And so we compare the geologic rates that are reported in the literature to the GPS rates that we determine from our block model, and you can see if they were identical, they'd fall on this line. And they're very close. They're very close. And these are ages of up to 2 or 3 million years for the Gulf of Aden, Red Sea, hundreds of thousands of years for the major faults. So we've got measurements that were made over 20 years that are giving us results that are consistent with million-year measurements. Now now who knows what an Euler vector is? Okay, not many. So look, you can, if you have a plate and you want to describe the motion of this plate, all you need to do is have a place on the Earth's surface, location, and a rate at which this thing may be rotating around that plate. Even if it's translating and not rotating, you can describe its motion around a pole. So that's called an Euler vector. The vector is 3 components, latitude, longitude, and the rate at which it's rotating to describe the motion of that block. So you can do this for the Red Sea, and you can determine the Euler pole between these 2 plates. Turns out to be up here somewhere. So that if you have a pole in the ground here and you rotate these plates, they're going to move away from each other around this pole. And that's what that describes precisely, if these plates are not deforming, the relative motion between these 2 plates with three numbers. So that's what has been done here. And this is a study using magnetic anomalies, about 3.2 million years average. And you can see the pole location, latitude, longitude, and the rate of rotation. And this is from our paper we did in 2006. And you can see they're identical. In fact, they're too close because they're much better than the 1 sigma uncertainties. So over 3 million years, we think we're measuring things that are happening over 3 million years with 20 years of measurements. 10 really, 10 years of measurements. This is an order, 6 orders of magnitude extrapolation. It's crazy, really. But we can do a little better. So here's a figure from a study done by Nadine Macquarie and her colleagues at Caltech some years ago, 2003. And they plotted the location of a point located on the Arabian-African plate. Okay, so Arabia and Africa, before the Red Sea opened, were 1 plate. Okay, so this is Arabia and Africa here. And they determined its position at these different places using the magnetic anomalies in the Atlantic Ocean and other geological observations in the collision zone. And so somewhere between here and here, the plates separate. That's the opening of the Red Sea. And just by 21 million years, you can just see a difference between the motions of these 2 plates. So now there's 2 plates. And then they track the motion right through to the present day. Okay. Now this is the GPS rate that we determine today. And what you see is it's identical within 1 sigma uncertainty out to 11 million years. So Nubian plate has moved at the same rate it is now for the past 11 million years. Meanwhile, Arabia also has moved without changing its rate significantly, certainly for 11, and maybe all the way back to when it started to separate from Nubia. So we can extrapolate our measurements back to tens of millions of years in this case. But what do we see here? This is an incredibly important study that these guys did, and to me, for my thinking, the way I understood this problem. And it's this, that we have Arabia and Africa, remember what's going on here. We have Arabia separating from Africa, and meanwhile Arabia is crashing into Europe. Well, what separates Arabia from Africa? Slowing of Africa. So it's not that Arabia pulls away, it's that Nubia falls away. So Nubia slows down, Arabia keeps going almost at the same rate, maybe a little slower. That's going to turn out to be important too. Maybe both plates slowed down when the Red Sea began to open. This is a curious observation. What kind of mechanics could do this? This is the kind of thing that we think may lead us to understand what's going on here a little better. So if we break this thing down a little more, and it's the same picture basically, the result I want to take out of here is that the rate of extension here between Nubia and Arabia changes by a factor of 2 between some time when it started rifting and 11 million years, and between 11 million years and the present time. Okay. So with this, we think we can go back. Let's see, can we close up the Red Sea? Can we close things up? Can we turn everything around like a jigsaw puzzle and use these numbers to put it back together and see what we get for an age for when this started? And then we can compare that to the geologic observations. And that's what we try to do here. And so all we're doing here is we're saying, okay, we have good velocities at all these places. Now this picture shows the motion of Arabia with respect to Nubia. Okay, it's a little different. This picture here shows the motion of Arabia with respect to Somalia. Okay, again, it's a little different. So all we do is we measure these distances. Okay, this is how much we think the rift has opened. And we do a little bit of algebra combining these two, since things happened at 2 different rates. And we can estimate the time when the rifting began. And that comes from the slope of this curve plot of the opening width versus the rate at that location. And when we do that, we get about 22 plus or minus 3 million years. It's a little on the young side, but basically in the ballpark of somewhere between, their numbers reported in the literature are between 20 and 30 million years. So the main thing is consistent. So we've got a consistent picture here. In other words, those rates that we saw that were deduced from other kinds of observations give us a consistent picture with the structures that we see that were developed. Okay, well, we can go, what's this? Oh, I must have left next. So we did, excuse me, you're my guinea pigs. This is the first time I gave this talk. So we can do this in a little more detail. Look, we have some ideas that look at this rift here. Can we estimate how long it took to open this rift? Look at this structure here. It's a this goes right up into the Dead Sea Fault. I think I took this slide out. Goes up into the Dead Sea Fault. We can estimate, we know the offsets on the fault, we know the GPS rates. So now we can start using our very precise GPS measurements. We're measuring things to tenths of millimeters per year. Geologists don't have that resolution in their measurements. So can we use these now to do geologic stuff? And if we can, we've made a big step in terms of being able to quantify, processes that geologists have been studying, for years. In fact, I had a guy jokingly get mad at me. He said, "You guys, you come in here in 3 years, you tell us what the slip rate is. I've been working here 20 years, and I haven't been able to figure it out." It's much, much more difficult to go out and date things and measure their offsets and all the other problems that can come in. Anyway, so that's what we're trying to do here. And when we do this, and I'm not going to go through it because it's too boring, but if you look at the offsets, like, for example, the Dead Sea Fault, you look at what the offsets are, you look at what the slip rates are from GPS, you get an age. I mean, it's very simple. You look at the offset on the southern Dead Sea Fault, the present day slip rate, you get an age. Turns out these are about the same. And this is very, very curious because one is offset quite a bit more than the other. And this is an area of active research. I may have something in my next slide. I don't remember I left it in. Sinai, here, look, this is an offset. This has clearly just been offset here. So it's offset about 50 kilometers. GPS rate is about this. That gives you 11 plus or minus 2 million years. Now, don't forget that number, 11. Remember, we got that 11. That's when everything was changing in terms of the plate system. That's when Arabia started moving away, or Africa, Nubia started moving away more rapidly. So this is a time of change, 11 million years. And we get a number of different ways, and this is, in essence, 11 million years. So everything in here is changing around. The whole configuration of what's going on here is changing around at about 11 million years. Well, we can also say, well, wait a minute, this is before 11 million years. Well, remember, the rates change by a factor of 2. So we can use the rates now and say, okay, well, and all of this deformation was on here, and it was half the size. We can get an estimate of how long it took for that thing to open up. And it comes out to somewhere on the order of, I think this number's too low. I think that's a mistake. But it's 13 plus or minus 4 or 5. 11 plus 13, so the whole thing opens in 24 million years. That's the age of the initiation of opening of the Red Sea. Everything's fitting back together within this very simple kind of scenario where things changed very quickly at 11 million years. Started somewhere around 25 and changed at around 11. Okay, yeah, this is, I'm not going to go through this in detail either. This is the new velocity field made like this, and you guys who've been looking at this stuff, because this is all new data. This is quite remarkable considering what's going on in this part of the world. We're really happy we managed to finish this up in a couple of years ago. But we have a remarkable velocity field now across the Dead Sea Fault. But look at this. This is half what it is down here. It's half of what it is right here. So there's something funny going on, and this is a new discovery recently. Something must either be going offshore or something. Something's changing, and it's not changing over here. We know that. So next, stay tuned, because there's going to be a change in the Dead Sea Fault. It's going to have a splay somewhere up here, and Paco is a good friend and partner in this work, is writing that paper right now. And again, we come out with 11 for the age of the Dead Sea Fault. Okay, so here's the southern Red Sea. Okay, now the southern Red Sea is very, very interesting. Look at these GPS. Again, these are our GPS stations. Okay, now here's what we have: the triple junction, what's called the triple junction. We have a Red Sea rift, we have the Gulf of Aden rift, and we have the East African rift. And this complicated area is called the Afar triple junction. And now what we have today going on, look what's going on today. Here's Africa. Look, it's not moving. Okay, good. Right here. Now, this is the Africa reference frame. We're looking at everything with respect to Africa, so it better not be moving here. But look, as you go down the coast, the rates increase, increase, increase. By the time you get down here, this is moving the same as Arabia. So what's going on here? Here, what's going up here, all the extension is right here in the middle, somewhere in the center part of the Red Sea. Okay? As you come down here, some of the extension gets shoveled off into here and gets more and more and more and more until by the time you get down here, it's all of the extension. Meanwhile, all of the extension's here, and now it gets slower and slower and slower until it's gone. This is now inactive. This is basically part of Arabia, even though there's still the Red Sea between it. So we can do some more tricks here. We can say, okay, well, where's the Euler pole? You're going to learn that. That's an important one. Where's the Euler pole for this rotation of this block with respect to Nubia? Well, it turns out to be here. And you can see that point is basically perpendicular to all of these vectors. So that if you rotate that block around here, you'll fit this very, very well. So we rotate it back. And if you rotate it back at this rate, because the Euler pole is the location and the rotation rate, we wind up crashing into the continent after about 10 degrees at this rotation rate, about 5 million years. So at 5 million years, you basically crash into the continent. Now what happens here? Now we have to make some assumptions, because you can't keep closing it, because if you do, you're going to have this, you know, it just doesn't make sense. You're going to be shoving this stuff all the way into Africa. So you have to change where the pole was located. So we hypothesized the pole was here. Why? Well, because we don't have anything much better to hypothesize, and because that allows us to continue this rotation back in without getting a lot of overlap between the block itself, which is not extended, and the unextended terrain ground in Africa. Okay, if we do that, and we assume that this point was attached here the whole time, then we can close this extra 25-degree rotation at the same rate. With this, again, the rotation rate is determined by assuming this is the same as it was always attached to Arabia. You get 6 million years. So folding this all the way back in suggests that this started 11 million years ago. Again, 11 million years. So everything seems consistent. And what's happening here? The rift is going from this orientation to this orientation. It's getting more north-south. Remember what's happening in the north. It's going from the Suez, which was like this, in fact, exactly like this. It was on this exact line, to the Dead Sea, which is like this, more north-south. So you have a temporal coincidence and a spatial coincidence in terms of the deformation. 11 million years, plus or minus, seems to be when things happen. So I'm not going to go through this. In fact, I didn't know it was in here like this. I thought I changed it. But this is sort of the scenario. We've got two phases. Now, what happened to make Arabia? Why did Arabia rift off of, or why did Nubia fall off from Arabia? Well, that's the big question. But two things happened. One, before the rifting started, there was a gigantic volcanic eruption at the location of the Afar that covered huge areas of Africa, Arabia, Somalia. This is believed to be due to the African hotspot. Okay, this is maybe the first hotspot identified on the planet after Hawaii. So this is a very hot plume of stuff coming up and cooking the lithosphere. This happened just before the rifting began. Red Sea rifting, as we just went through, began sometime around 25 million years, maybe plus or minus. Meanwhile, the East African rift, remember, that's this extension down to the bottom. There's no, okay, I really haven't gotten to this, and probably it's confusing, but forget about it. Remember, I told you in the beginning, we're gonna convince you that subduction is pulling everything. So if subduction is pulling Arabia, I'm sorry, let me go back. So first of all, the East African rift is extending between Nubia and Somalia. There are no subduction zones to pull them apart. Meanwhile, it goes very slowly. If you didn't follow that, don't worry. But something happened at 11 million years. Okay, so first of all, this 30 million year event, we're saying that weakened the plate, that allowed the Red Sea rift to open, that allowed the plates to separate. Now, what happened at 11? So that was somewhere around 30, 25 million years, and it started the rift. We'll look at why. But at sometime between 16 and 11 million years, something else happened, and that is the Gulf of Aden. Remember, it runs more or less east-west. That's the boundary between Arabia and Somalia, became a full ocean ridge. In other words, the lithosphere became completely broken, and hot molten material was erupting at the surface. So what we're going to hypothesize is that subduction is driving the whole system, and that when the Gulf of Aden rift completely broke, it allowed Nubia to fall away. In other words, it removed a part of the pull from the subducting plate north of Arabia from Africa. So it's no longer pulling Africa, it changes the balance of forces on Africa. Africa slows down. Now, things are, some of these questions are a little more subtle. So because this is funny. Now think about it, what you've got going on here. You've got Arabia getting ready to collide with Eurasia, and you've got Nubia along for the ride, both of them subducting. Arabia starts, Nubia, you get a big volcanic eruption, you weaken the plate, and then Arabia continues at the same rate, and Nubia slows down. So the idea is, and in fact, even Arabia slows down a little. Remember, you saw that. Arabia slows down a little. So what's going on here? What I would suggest is, what's going on here is that the slab is getting pulled, is pulling the plates. When the thing breaks, it's not pulling Africa as much, so Africa slows its northward motion. But meanwhile, why doesn't Arabia go flying, right? It just dropped this gigantic plate, which its piece of its subduction zone was pulling, right? So if you drop a big weight, whoa, it should go flying down the trench, right? It should go flying and collide. Well, the only way that, and it doesn't happen, it slows down. So why is that? It must be that there is virtually no, very, very low resistance to pulling the plate. The plate has enough strength that you can transmit stress through it, okay, until it gets too weak by that volcanic eruption. But it can't be resisting too much. It's resisting some because it slows down, right, when the force goes away. But it can't be resisting very much, or else Arabia should go flying on off to the north, and it doesn't. The only way I can make sense out of this is that the force balance is almost exclusively in the mantle. That is, you've got the weight of the plate pulling us down, right, pulling everybody behind it, and you've got the resistance in the mantle itself. So it doesn't even care if the plate has is pulling a big gigantic plate or pulling virtually nothing. It's going to go at the same rate. It's just falling into the mantle, and the forces that are pulling it are balanced by the forces that are resisting it in the mantle. So that is what we would suggest is going on. And I don't think everyone would agree, but I think it's worth, we'll see if it's true or not. Now, of course, that's the wonderful thing about science. We find out what's right and what's wrong in the long term. Okay. Let's see. Okay, getting close to the end here. I'm going to start stepping back and back and back from a bigger and bigger picture, and I think it gets to be more and more fun, so hang in there. The basins in the Mediterranean. Remember what's going on here now. We've got Nubia falling away. It's not moving away, but it's going more slowly. So before 25 million years, so 22 plus or minus 3, this is the rate at which you had convergence of Nubia with respect to Eurasia. Okay? Where's the velocity? Here, velocity. So it's about 20. Then at 11 million years, it slowed down to about half. Okay. No, excuse me. This is pre-25 million years. Then at 25 million years, it went at this rate until 11 million years, and then it slowed by half between 11 and 0 million years. Okay. So between 2000 and yeah. So we've got this plate slowing in 2 steps. This convergence is both plates, right? This is before 25 million years. There was no Red Sea, so everything's moving this way. Now, point is that these basins in the Mediterranean opened at about the same time, 25 million years, 21. These are taken from the literature. And there's a change, deformation jumped from one basin to another at about 11 million years. And there was 2 phases of extension in the Aegean. Again, all taken from the geologists. So this is another indication that it's slowing of this plate and and the change in the subduction, rate of subduction, that's causing extension in the upper plate. And the mechanism for this, this is, okay, this is the North Anatolian Fault. Okay, we'll continue. So I'm going to go a little quicker here. So look, this is the velocity field for Turkey. See that? 0, 0. These are basically 0, and these big guys. So this is the North Anatolian Fault. And remember what we said, it's about 11 million years old, and it changed the situation in eastern Turkey. Well, here's the situation in the Aegean. And if you do the same kind of games that we played earlier, you can estimate the ages of some of these structures. Like this is an estimate of the age of the Marmara Sea. It's a pull-apart basin at the end of the North Anatolian Fault. This is the North Aegean Trough. So we can estimate all these ages, and what we come out with is very young ages. These are quite young. So these features formed very recently, and these features are basically 3-4 million years old. So what's going on here? Well, we would suggest, so here's what the Aegean looks like now. Okay, so here's what I was saying before. This is the same velocity field. Okay, exactly the same data. But now we're minimizing the motions in the Aegean. So we're seeing everything as if you were standing here in the Aegean. And first of all, you can do it. In other words, these vectors are all quite small. And the fact that you can do that, you can't just do that. You can only do that because there's no motion between these sites. So what this is saying is, wait a minute, this is an area that's a basin, it's extended. You know, why isn't it extending? It's not extending. It's moving as a coherent unit. And so what we would suggest here is what happened was, originally, when there was an indenter over here pushing up the mountains, this area was extending. And it used to be up here, this arc. And now it's extended all the way down to here. But at some point, this fault broke across the north part of the Aegean Sea, and then this pull that was extending this plate just moved the whole thing uniformly, with all the deformation being controlled up in the north. So again, it's a change in the kinematics, the change in the motions, that can give you some idea about what the dynamics are. And now we're all together because I don't remember any more we got going. Oh yeah, so let's go back one. So just step over just a little ways into here. This is called the Esparta angle. This is the Hellenic Trench. This is where you have subduction of ocean lithosphere. Here we think there's some kind of subduction going on, but it's not as clear. But let's look at that area. And here we're looking at the same velocities solution, but now we're fixing Anatolia. So look here. You see these small vectors here. Okay, so we're trying to look at the motion of this corner of this block with respect to the Anatolian plate, which is around here. And what do you see? You see extension towards the sea. You see motion and extension towards the sea. Well, this is where the Cyprus arc is, and we would suggest this is being caused by rollback of the subducted slab. And the physics of it is very simple, and all of you will at some point, if you take a geophysics course, use this text, Turcotte and Schubert. It's really humbling to see what these guys managed to do in their careers. They're a quite brilliant book. But this picture, you go to the book, because I'm not going to have time to tell you the whole story. But the bottom line, this is what I was talking about before. As the plate sinks, it induces currents, and these currents hold the plate up. And the strength at which they hold, the force they can apply to the plate is directly proportional to the velocity at which the convergence is occurring. So as soon as this velocity slows down, this plate, the pressure on this plate holding it up will reduce and the plate will sink. When the plate sinks, it instantly opens a huge hole which drags this plate, sucks this plate right on over it. That's the opening of the back arc basin. And that's how you can get such rapid motions of these basins. They fly open because it's almost a phase effect. This thing sinks a little bit and it opens a big hole here. So this is what we think is going on. This is what we think is driving the plates, the pull of this subduction zone, and we think this is also driving the deformation in the overriding plate. So how far can we push this? We can push this all the way. So here, this is a compilation. This is from Zhang et al., 2004. This is the velocity field we've been looking at. And look, there's some similarities here. We have this collision. We have this butterfly-type pattern here. You have the collision of India. You have this pattern. Is this related to the Sumatran arc? Is the Sumatran arc rolling back and sucking out part of Tibet? Much more complicated because you've got all kinds of subduction and stuff going on over here as well. But it looks like there may be some similarities. This is from a paper by Richard Almendinger, and this is from a recent compilation from Philippe. So, to what extent is subduction, this is the conclusion. To what extent is subduction driving the plates? Well, we think it's the most important thing. And I like this picture. It's published in 2011 paper. But I like this because it shows this is a hypothetical boundary between the plates in the south, Africa, Arabia, India, Australia. And this is the rates. If you put all the motion on one line, this is what it would look like. And the point here is how uniform this is. These are separate plates. There are differences along their boundaries, but these differences are very small. They're 10% maximum. So for the most part, this is like one big windshield wiper sweeping across here, closing up this ancient ocean. And we think it's the pull of this sinking lithosphere that's totally responsible for this. And that has some implications for some mysteries about it. For example, why is India still crashing in so fast when it shouldn't have a slab attached to it this late in the collision zone? Why didn't, as we said before, why is there's no basal traction on Africa? And why isn't Arabia slowing down? It's crashing in, pushing up mountain belt. So these are all questions that you guys, I hope you have a chance to address in your future careers. Thanks. Sorry I ran over. Well, our work, first of all, there have been big earthquakes in Istanbul. And there is strain, we think, accumulating on the Marmara segment of the North Anatolian Fault. But this is a mystery. And it's something that I think UNAVCO, I hope we get funded to look at some of this question. Because it appears that after the 1999 earthquake, that the behavior of the fault has changed where that earthquake occurred. And it looks like it's creeping now. And it may be creeping it is creeping now at the full rate of full strain accumulation. So all the motion is being accommodated without any stress being accumulated, or strain or stress. But we don't know under the Marmara Sea exactly what's going on. What we do know is that when you get on the north, you get near the fault, you don't see any strain accumulation north of the sea. And it's was a very, very unexpected result, because we know that at least some earthquakes have occurred near enough to Istanbul. They could have been on that fault. This is the problem. 1755 was a big earthquake, but where exactly was the fault? When it's underwater? And so, yeah, this is a very interesting problem, and one that we have a chance of, I think, gaining some knowledge about in the near future.
So, Rob, the map, the velocity field map, is a beautiful thing.
Yeah.
It shows a pretty clear motion.
I know, I love it.
Over the course of your career, assuming that it hasn't always been that clear,
Surprises? Oh, yeah. The biggest surprises for me was the fact that the Aegean was not extending. I expected it would be extending, but that's because I wasn't so clever, because if you look at the seismicity, it's aseismic. There's a big hole there. There's no seismicity. The other big surprise was how undeformed the collision zone is, where the Arabian plate hits Eurasia. I mean, I even published it in our first paper. Oh, we expect to see this, strain distributed across the collision. No. There's large areas that are just coherently moving in a coherent fashion. And it looks like they're either subduction type process occurring along the Caucasus, but it's not what I expected. And I never expected to see the rates increase the way they did in Anatolia. I expected it was being pushed, and I expected to see compression across the East Anatolian fault. Chuck? Oh, excuse me.
Sure. I was a little confused.
Me too.
I feel like your major operating hypothesis is that slab poles, the major driving force. And on a lot of the maps we looked at, the major movement was into that subduction zone in the opposite direction in the west, right?
Yeah.
Wouldn't you expect, maybe for reference issue, wouldn't you expect most of them forward?
Okay, good. Yeah, so look, at a subduction zone, you can have a couple of things going on. If the plate is, like in South America, for example, if the plate's moving fast enough, it's not rolling back, it will cause compression in the overriding plate, and it'll push everything. So everything here will be moving, pushing back, being pushed by this plate until the earthquake occurs, and it'll pop back out. So you get big compression, though, okay? But if the plate is falling, then it's pulling the plate, overriding plate. So it can do two things. And the plate's falling when the rollback is more than the rate at which it's progressing. That's what's happening in the Hellenic subduction zone. So that's pulling everything towards the trench. But that's a good point. Good point.
So why was there this sort of easy shift in that slab pole?
I know what you're saying.
Because you're saying that the decrease in slab pole decreases velocity, but also a decrease in velocity of the Nubian plate would allow for slab pole.
I don't think I understand that. I thought I understood the beginning, but you lost me.
Answer the question you thought about that.
Well, give me one more shot at it, please. Give me that again.
Okay, so there are two ways to do this.
Right.
Have something happen with the subduction slab, the slab pole decreases.
Okay.
Decreases Nubian plate flow.
Okay.
Alternatively, Nubian plate flow.
Okay, I think I understand. Here's what we think happened, and I'm sorry I was getting a little confusing at the end. We think what happened was that the reason that there was an event, which was the plume, that weakened the plate. Meanwhile, all this time, you've got subduction going, getting pulled by the neotethys under Eurasia. The plume gets weakened, and then this piece of the subduction pull basically stops pulling on Nubia. So it's only got its own little piece of subduction pulling it. So it hasn't got as much plate force pulling it as it did before. Then at 11 million years, okay, that's 25 million years. So you would get your initial lessening of the pull of that subduction because of weakening of the plate and continental rifting. Then you get a break into full oceanic rifting, and you even more reduce the amount of pull that you can transmit across the rift zone. So you have a second episode of lessening of the pull on Nubia in Africa.
And you think that this is operative at the several thousand kilometer trench parallel, like you showed, between Africa and Hellenic Basin?
Yeah. I think, if I understand your question. But we can talk more because I see you're a skeptic, and I'm eager to hear other ideas. That is good.
My comment is just simply it's been the strength calculation
Yeah, well, this is the problem with the math, you see. This is the problem with the math. You can't do the math because you don't know the parameters. So you can make it work out or not, you know, depending on what you decide you want to make the viscosity of the asthenosphere, or the strength of the lithosphere.
The mantle driving forces, which Goshen and Holt actually have looked at, and I would say that their result for Africa is very interesting and perhaps corroborates what the points that you're making.
Okay, I should look at that.
Yeah, it's a cool paper. Okay, one last one, Christine.
Oh. How large? I'm sorry, the what? Yeah, I heard that. Oh, okay, let's see, can we get a picture of it? I don't want to keep people, it's lunchtime. I mean, the worst mistake you can do in a seminar is go over in lunchtime. And I don't know that it's going to, wait, here. That'll do, right? Well, let's go back. Okay, so that's, this is, so the FR is this triangular region in here, okay, and it's all very low and hot. This is below sea level here. It's all volcanic and, oh, is that what you want to know? Oh, yeah, well, the plume is an interesting thing. I mean, it apparently came up in the south and moved to the north, which, I mean, plumes are controversial still. I mean, most of our community, I think, agrees that they exist. But, you know, there's a whole school of thought that, you know, this is all lithosphere, that the plumes is just an area that the lithosphere cracks and stuff comes up. But I think with tomography now, plumes are getting a pretty good foothold. But, you know, a plume is a whole nother, you better invite Kevin Burke or somebody to give you your seminar on plumes. That's a whole nother story. Thanks.